All right, so live stream running. Start in a minute. Hello, everyone. Hello, welcome back. Hey, guys. While the last few people are taking their seats, few bits of housekeeping again. Is it loud enough? Can put up the volume a bit. I don't know if that's. Tell me if it's too loud or not loud enough. You may have seen, or you should have seen, the announcement on COMP526. I released the first class test on Canvas. Some of you have already done it. So can I ask for a bit lower volume? I don't want to shout over you guys. Silence, please. Okay, I'm got a bit closer to the mic, I guess. Class tests. There will be several, at least a handful of those spread out over the term. So each individual one is not so critical. And hence, it's auto-marked and just pass-fail for one question. You have the practice version, though. So use that to check if you understand what's asked and what the format of the answer should be. In the first case, it's just multiple choice, so not too much. Hope that works for everyone. If you do have some genuine technical issues that Canvas crashes or stuff like this, it once in a while happens. So let me know. OK. I will come back to the halfway serious questions on Slido in a few minutes. But you probably want today's attendance code as well. And since you're getting your phone out anyways, you can copy paste the code from the question if that's shorter. But I think it helps if you log the got it so that I roughly know how many people to wait for the future questions. So we can, if we have to do the attendance code fun, we can at least get some useful information out of it.
Someone's asked if the live stream's on.
It should be. Yeah, live stream should be running. So the questions are a few minutes ago. Maybe I started it just shortly after that. But thanks for flagging it. Anyone still fiddling with Slido? Let's ask the other way around. Who's done? Who are the 88, 94 people? Right. Not too many still typing. Let's suppose you're done. We're in the middle of Unit 2. If you recall, that was on some fundamental data structures. So some... sorry, guys, I really don't want to scream over you for the entire time. If you want to chat, wait till after or leave the room, or I'll have to come closer to you guys. That's fine. We were talking about some fundamental data structures, so solving some key problems that are used over and over again in computer science. If you've done an undergrad degree in computer science, you will have known all of those, and part of what we do today is finish that off with the binary search trees, and then we'll branch into sorting. Again, a fundamental topic that many of you will have seen, but there's a few things in the next unit that I don't think most of you have seen. So the second and third part, at least. The last part of Unit 2 is about symbol tables and about binary search trees, which arguably is the most useful and most fundamental of all those data structures we covered here. And so I think it's particularly useful to know about. It's also just a beautiful piece of theory that this works. I mean, you get used to it so much that maybe it loses all the marvel and wonder, but it's quite a feat that it's possible. But let's first talk about the abstract data type that comes with it. I asked you this fun question. Let me switch back to it briefly. So you're not young enough, or at least old-fashioned enough, to have used a physical printed dictionary. Of course, the reason why I asked about this is, how do you find a word in a dictionary? And we'll come back to that. So first of all, let's get some terminology straight out of the way. So we have symbol tables. That's the way I call them here, and that's the way they're called in the algorithms book, the red book that I recommended you to read along for this unit if you haven't had this in an undergrad course. But there are many other names for the same thing. It's important just to know that these are the same, okay? So symbol table, sometimes called dictionary, including in Python. In Java, it's called a map. It's sometimes also called associative array, or key value store is essentially the same. Often people mean a distributed database instead of something on a local computer, but it's by the API the same thing. So the key thing we can do with this, and this is dynamic, you can change it over time. You can put a mapping into this symbol table where you associate a value v with a key k. And in Python, you would just write it like this for a dictionary. That is also why it's called associative array sometimes, because it looks by the syntax like an array, but the thing you put into the square brackets is not a number, not an index or an offset, but some arbitrary object. Then if you have a key, you can look up what the value is that's associated with this. And symbol tables are fundamentally single valued. So every key is associated with one value, or maybe no value if it's not contained. But if you call put several times with the same key, it will just overwrite the previous mapping. You can also remove a key and its mapping again, and you can check whether something contains a given key, whether a dictionary or a symbol table contains a key. Of course, you could also check what get returns, and if that says, I don't have a mapping for that key, you also get the same answer as for contains. That's just to make it more readable. As I said, it's a fundamental building block for pretty much. I can't imagine a program that doesn't in some way use one of these data structures, indirectly at least. Very fundamental. And okay, I don't think I know a programming language that doesn't have a library that contains a symbol table in one form or another. Now, there are many esoteric programming languages. Maybe there is one out there, but not. If it's in practical use for real-world problems, it will have a symbol table. It's useful to make the distinction between symbol tables and mathematical functions, because they're, in a way, very similar. Both you give a value and then you get a mapping. You put a key in and get a value out. For a mathematical function, we say also you just put one key in and get another key out. So they look a bit similar, but the big difference is if we think of mathematical objects, we think of them as immutable. These are values that don't change. If you take the number 5 and add 1, it's no longer the same number 5. It becomes a value 6, but the 5 isn't changed. Whereas data structures in computer science, and specifically our symbol tables, we assume that they can change. So you can change the mapping of a key. So you can think of it as a dynamic function or dynamic mapping if you want. Just want to get that, make that clear. So it has this similarity to functions, but changing over time is the difference. So we have a new abstract data type, the symbol table. How can we implement it? What kind of data structures are there to implement it? Now let's look at the simplest possible ways first again. We could use an unordered list, say a linked list. It shouldn't matter that much. I can hear me a lot. Is that still loud enough? No complaints either way, so I'll take it as a yes until someone complains. Let's take an unordered linked list, and when we put a new key value mapping in, we just stuff it at the end. That's fast. Yep. Oh, unordered here just means I don't care about the order. It's in contrast to the other option that will come. So what it means is I keep you say put hello 5. Then I'll just create a new entry in my list that has the key and has the value. And it's somehow linked with pointers. So if you do another put A0, then I'll just add another thing at the end of this linked list. And there's no specific order maintained in the list. The newest thing is just at the end. That's the way it's meant. It's not sorted. It's also not random. We don't deliberately randomize it. It's just the order in which it is inserted. But unordered here stresses the fact that we don't specifically impose an order. That's all it says. So you can't guarantee anything. Which means put is fast because you just put it at the end of your list. But if you want to find the mapping for a key, the best thing you can do is just go through all the mappings. Check with each key, is this the key that I'm looking up? If no, you keep going. If yes, you return the mapping that you found. But actually, even in that case, you have to go through the entire list and check if there's another mapping with the same key, because you should return the newest one. So there's a second problem lurking. This might grow over time, even if you just put in the new key. So you might need some cleanup calls and so on. I'm not even listing the details here because this is so slow, it's not interesting. If that's the best we could do, symbol tables wouldn't be a thing. The other alternative that we have is using some sorted thing. And I put here again sorted linked list to emphasize this. Because if we want a sorted list, but we want to insert something in the middle, we can't really use an array. We've had this problem last time. We discussed it in a bit. So you can append to an array using this doubling array trick, but you still cannot insert in the middle of an array without moving all the elements. So either way we do it, either linked list or an array, will actually get us linear time worst case for put, even if we know where we want to go because we have some fast way to find it, it doesn't help. If we use a linked list, then certainly also get is just as slow as before. The sortedness didn't really help us there at all. Right, sorted here means sorted by key. Although, because it didn't help here at all, it doesn't actually matter. But going forward, sorted will always mean by keys. But I'll comment on that again. So the strange observation here seems, at first, sortedness doesn't help us. Because just a simple way, maintain something like an array. where you can quickly access elements by index, but also insert in the middle. That's already a tricky problem that we haven't really solved so far. But we'll see binary search trees actually solve that. Yeah, that's the point. It would help us if we could somehow jump into the middle, right? I know you all know this, so let me move ahead. There's of course this thing called binary search, and I asked you about the physical dictionaries because of that. How do you find a word in a dictionary? You do something like a human-guided binary search. I guess no human does exactly binary search, like opening the book in the middle, checking if you're to the left or to the right of the current page. We do something with the starting letters, but it's not too dissimilar. But let's, to be self-contained, let's briefly go through this more formally. So if we have somehow an array of sorted elements, and here I'm only listing the keys. There is a second array that associates the values with those if you want. We'll ignore that for now, as in the case of the heaps, because it doesn't actually make the data structure more interesting. So here we have these keys in sorted order. Let's try to search for some key, say 69. So what binary search would do is you jump into the middle. That's this M. Index M is basically the middle between L and M, somehow rounded if it's between two. So here we would have checked 63, and 63 is less than 69. What that means, because of the sortedness, is everything that's left of 63, including 63 itself, is excluded. If 69 is in the array, it is not in the left half, because all of those are too small. That's the key trick of binary search. And then the rest is just putting this into a nice recursive algorithm that nails down the remaining range of the array. So after this, we can update L to the position to the right of that. Then we get a new M, so we can again do one comparison with that. Now that's bigger than 69, so we know the 80 and everything to the right is excluded. If 69 is in the array, it is not in the right part of this, in the right half of the right half. So we narrow it down further. We do another check, 77, still too big, so we exclude again these two. And then we've narrowed it down to a single value that we can just check. And in this case, of course, we find the 69. That's binary search. I hope this wasn't new for anyone. I hope also it wasn't too boring for anyone. So what we do is, in each step, we roughly halve the remaining number of elements, plus minus 1, because we can't, if it's an odd number, we can sometimes not work our way around it. But if you do the math a bit more careful, the number of comparisons, so the number of times you have to check something against your key that you're looking for, is at most log n, the number of things you have, rounded down plus 1. Okay? That's the number of times you have to cut n in half before you're at 1, by and large, and then the plus minus 1s, you have to do the math. So that's good. That's great, actually, right? Log n is very small compared to n. And all we previously had linear time get or put. So that's great. It comes with this restriction or this caveat. What we needed to do binary search is being able to jump into the middle of the array. And insofar, sortedness helped us for this. But sortedness is a problem if you want to insert into this array and it's still an array. So far, all we've seen was either random access with an array, where we can jump at any position, or quick insertions in the middle, but then it's a linked list and we can't use random access, as I called it here. So random access is maybe a slight misnomer. It should be called fast access by index. But that's why we call RAM. RAM, it's the random access memory, where you can do accesses by index fast, as opposed to old magnetic tape, right? This also existed. So it's maybe not the greatest term, but it's so established that I kept it. What's meant is you can jump to position 17 in one go. Good. Everyone with me? So we'd like to have this fast search, but we can't really do it with an array. In the next section, I'll show you a solution to this problem. Maintain an array that you can fast access by index, but also change. That's not usually how binary search trees are presented, but I think that's the key abstraction that is actually often so useful. They have other uses, though. So let's talk about binary search trees. Before we do that, let me again check what the audience already knows. As the attentive listener may recognize, the same set of answers as we had for the heaps. So we had something like 110 earlier, 118. Okay, it seems most people got that right. Remember, number 3 was the heap. It's a subtle difference between the two. So this one, that's what we called a heap ordered tree, referred to last week. Binary search tree is this one. We'll discuss it in detail. So as I said before, think of them as some magic solution to have a dynamic sorted array. I'll explain more what I mean by that. What is it, though? So it's, again, a binary tree, which is the same beast as we started with for heaps. It's any kind of structure where we have nodes, and they have a left and a right child. And both of those can be empty. Now, I didn't go into this detail before, but maybe it's useful to have something closer to programming syntax. So if you think about a UML diagram for some class that represents such nodes, for our symbol tables, it would probably have these 4 fields. It would have a key that it stores and a value. And then it would have a pointer left and a pointer right. Remember, either of the two can be null, so then the node doesn't have that kind of child. In the following, I'll draw the null pointers like this. A little square means there's nothing, and the circle means this is a node. Good. So a binary search tree is any binary tree with the following restriction, namely that it has this search tree property, or the search tree order, which refers to the keys. Nobody can read that. All the keys in the left subtree are smaller than the key at the root, and all of those in the right subtree are bigger. Now, and that's true recursively throughout the tree, or it's true for every node and its subtree. So not just at the root, but in every point. Okay. Let me show you an example. This is a binary search tree with some keys shown in as numbers, in the nodes as numbers. In all of the following, we will never deal with the values. The values are always just carried along. I said it before. They don't change the data structure. So we don't show them in the drawings usually. And then you have a left and a right child indicated with the lines. Now, I want to point out that I drew the tree in a specific way. You can draw the tree in another way. For example, why did I choose to put node 12 so far to the left? You don't have to do that, but I think this is the one and only way to draw the tree that makes the sortedness visible. So it's drawn such that at every node, the entire left subtree is to the left of that node, and the entire right subtree is to the right. Okay, so I take the root, I draw this line down, and then left and right subtree stay in their lane. And that's true recursively. If you do that, that means you project down the keys to a certain x position. And if you do that, you see that that's a sorted order. And that's really nothing deep. It's just the search tree property, but you see it in action here. So that's the way to that will draw the binary search trees. I think it's very helpful to do it that way. Let's do an example of how you find a key in this. Let's again find our 69. Any search would start at the root because we actually don't have anything else from the binary search tree. The way we keep the tree in our hands is keeping a pointer to the root. So we're sitting here, and now we're comparing the key that we're looking for with the key in the root. 69 is smaller. So what we're doing looks very much like binary search, except that there's no explicit computing of the middle. We just take the root as some approximate middle. Right, so it's smaller. That means we go in the left subtree. And everything in the right subtree is, by the search property, bigger than 69 and can be excluded from further consideration. And we continue like this. 12 is too small. So in this case, we go to the right. 57, again, too small. So we go to the right. And in this case, we have found a node with that key. So if we do a lookup, a get in the simple table API, we would get the key, we would get the value that's associated with this. So we get the value field from that object that's representing the node. Let's do another example where we don't find the key. So if we look for 83, let's do it a little faster. We start at the root. It's bigger than 77, so we go right. It's smaller than 85, so we go left, but bigger than 80, so we go right, and bigger than 82, so we would go right. But here's a null pointer, so we know the tree stops there in a way. And that's the indication, we found 83. If it was in this list, it would have gone between these two keys, but it's not there, so it is not there, right? So it would return not found or some exception. Okay? That's the easy part. If we have a binary search tree given, then we can use it to find or look up keys. Now I promised that this is a dynamic data structure, so let's make it dynamic. The first kind of updates that we want to look at are inserts. If this is dynamic, we should be able to insert new things. So let's take, I should take a different color. I reserved that dark blue for corrections after this lecture. So I usually avoid using that color so that I have one free to do corrections in the lecture notes before I upload them in case I sometimes do something wrong. Let's do green. How do you insert into a binary search tree? The first step is we try to find whether the thing is already contained. So again, start at the root. We do the same procedure as before. And you can follow along. It would have gone here, but it's not there. That's good. We want to insert it. So if it had already been there, we would have to reject that. But it's not there, so we can make room for it. And the way to do it is in the program, you would just take this null pointer and insert a new node with key 88 there. In the drawing, I'll first have to make room, but all I did was move this over. I hope you can see if I go back a few times. I've just moved this around. And remember, the picture is just imaginary. What this really is objects in memory with pointers to each other. So there's no moving around to make space. They stay where they are. We just add a new object. There's the new object. And we put it in the right place. But again, in memory, it would be anywhere. And now we connect it with pointers to the previous one. And that way, it becomes linked into the tree. That's insert. And insert always works like this. You follow a path down, and if the element is not already there, you have to stop in some null pointer in some of these little squares. And then you can add your new thing into that little null pointer. We also want to delete keys again. If it's properly dynamic, that should be possible. Now, there's a few cases. Depending on what kind of node we delete, this is either easy or needs a little extra step. But let's go through it. If we delete number 11, key 11, of course, as always, we start by the search. And we find 11. Now, the important bit is this is a leaf in this case. A leaf is, I should have maybe introduced a little bit of tree and graph notation at this point. A leaf is a node without children. And we say parent and child and son or child. I try to use child as the neutral form. And then we have parent. Leaf is the one without children. What else do we need? Sometimes I say unary node for a node that has just a single child. Not sure how relevant this will be in this section. That should be probably all. So there's unary. If we have a leaf, the way to remove it is by just setting the parent pointer to null. So imagine this is no longer there, and you just replace that pointer with null, and gone it is. That's easy because there's nothing below it that would be disconnected from the tree. If we look at the second case, if we delete 69, let's do our search again. We found 69, so now let's get rid of it. But it has some children, so we can't just set the parent pointer to null. That would be wrong. But it has one null pointer. So what we can do is rewire the parent pointer to point to the single child of that node instead. So we get rid of the 69 and reconnect this. And then again, everything that was in the tree below this is still reachable. That leaves us with the last case, which is the only a bit more tricky one. So if we find a node that has the key we want to delete, but it's not a unary node and not a leaf, so it has two children. We'd like to do the similar trick. So we'd like to get rid of this node, but then we have two dangling children. Ah, shoot, what do we do with both? We can't link them both to the parent. So instead, we find the predecessor in sorted order. Remember, this is actually corresponding to this position in the sorted list. So it has a predecessor. Note it has to have one. If it has a left child, there must be at least one further node smaller than this. So it can never run empty. How do we find that? Oh, I circled the wrong node, you're right. Yeah, no, it's just a typo. Yeah. But it's otherwise correct. It's the right order, just incorrectly copied. So that's our predecessor, 82. Thanks for checking. How do we find this in the tree? We go one step to the left from 85, and then keep going right until we can no longer go right. In this case, it's a single step, but you can imagine in general, it might be, here's our node, then we can go here, 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 here. But at some point, it has to stop because we're running into that node in sorted order. There must be a last node, and then this one is our predecessor. Right, so we find this predecessor, and then we swap those two nodes or their values and delete instead this predecessor that we found. And the way the predecessor is defined, it means it definitely has a null pointer as the right child. So this doesn't recurse further. After we've done the single swap, we're definitely in the medium case, or maybe even the easy case possible. And so we can, the rest is done in constant time with changing 1 or 2 pointers. Question? He could have a left child, yeah. So 82 could have a, let's hypothetically, there's some other node and so on. That's all right. So we would then be in the medium case instead of the easy case. So when we delete this node, we would rewire its parent link to the single child. Yep. If you code this, you will actually not need to distinguish the easy and medium case. You're just rewiring a pointer, and it doesn't actually matter if that pointer is null or not. But I think it's a bit clearer to split it into 3 cases. Okay, that's all. That's binary search trees. So you can search, you can insert, and you can delete. That's pretty much all you need. You can build a symbol table based on that. I'll leave the details for the videos that I showed you or your memory from some undergraduate class. I want to briefly talk about how quick this is, though. That's an important part. Let's first analyze search. And for that, remember, so we have some binary tree. Let me add a small example without wasting too much of our time. When we search for, say, this node, the time this takes is to start at the root and follow the path down to this node in the tree. So the time for search is, if we want to be precise, say the number of comparisons we do of keys. That's exactly the depth of this node plus 1. Because at every node on the path from the root down to this node, we would have to do 1 comparison to check which way to go or whether we've already landed on the right thing. And here I'm essentially assuming that comparisons tell me 1 of 3 possible outcomes. Either one key is strictly smaller or bigger than the other, or they're the same. So it would be cost 4 in this case, and the node is, I guess we said, at depth 3 because that's the number of edges, so depth plus 1. So the number of comparisons we need is the depth of the node. Let's say that we call this x plus 1. Now, in general, it's hard to say how deep a certain node is, but we can upper bound this by the height of the tree. If I call the entire thing t. And we keep the plus 1. So if we know the height of the tree, then we know an upper bound for all the search costs. So if we want to be a bit briefer, let's call this h and understand that h is this, the height. And that's counting the number of comparisons. The rest of the work that we have to do is proportional to that. So you have to follow a few pointers, you have to access memory and so on. But in the big O terms, in asymptotic notation, big O of h is a precise statement for the total cost of the search. Now, if you look at what insert and delete do, they're also, so insert specifically is first a search, and then we create a new node and link it into the tree. So we already argued that this is at most the height. And the second part is constant time, with our assumption that the memory management is able to do that. But changing the pointers takes constant time on a RAM machine. Now for delete, there were the 3 cases, but in a way it's still bounded by the height. So you had one search, potentially the predecessor, and moving a few pointers. The last part, again, constant time. And the first and the second together are at most the height. Because remember how this worked? We were walking down the tree to some point. We wanted to delete that node. Either it's already fine because it's a leaf or a unary node, or we had to find its predecessor. But then the search would start at this node and go further down. So it can't in total be more than the height. Of course, we could have been lazy and said, search is at most order h, big O of h. Predecessor is also at most the total height. So it would be 2 times the height, which in big O notation doesn't show up. The factor 2 is just swallowed. But if you want to count the number of comparisons precisely, you could do, and it's bounded by the total height. OK. So in summary, this is also order h, right? Big O of h. So all the 3 operations are bounded by the height of the tree. So it looks like the height of the binary search tree is a really important parameter. To summarize for what we've seen so far, this also translates to the symbol table operations. As I said, coding this up is a little extra step that we won't do here. But that's what you get from this. Now, how high is a binary search tree? Unfortunately, the height can be very bad. If you insert keys and what happens is this, or even if it's a little less, it could also look like this. Depending on the insertion order of your keys, you could get a tree that's basically one long chain. And if you have that, the height is essentially linear, n minus 1. That's really terrible. That means all the operations are just as slow as what we've had before without all the fancy trees and so on. Oof, bummer. So what do we do? The good thing is that this is a very rare and somewhat degenerate case. And you almost never observe this if you have some randomness in your insertion order. So more specifically, if you assume that the insertions come in completely random order, so you insert the elements according to some random permutation, then you can show the expected height is logarithmic. And I don't want to go into the detail of the analysis here. This is a lovely topic, but maybe I'll spare you with it for now. You can make this statement much stronger. So instead of just the expected value of the height, you can get something that quantifies how unlikely it is to be above a certain height. So you can make a statement spelled out here in formal with formal quantifiers. Basically, whatever multiplicative factor you give me that you want above log n, I can tell you an exponent how unlikely that is. So in a way, it's a way to say not just the typical height is very close to this log n, also almost always it is if you have a large number of keys and they come in random order. Also remember, we discussed this in a bit more detail in the chapter on heaps. Any binary tree with n nodes must have at least this log yeah, base 2. Let me stress that here. So in this sense, what we find here as the typical height of a random binary search tree when you insert things randomly is very close to the best possible height. So it's not just okay, it's almost as good as if you perfectly balance everything out. All right. Let's do a very short break now before we jump into the next thing.
Just noticed the message.
Oh,
Sorry
right.
about
No
that.
worries. Yeah.
And I want to what I want to express is that at the end of I know it's binary search, but at the end the low bound and the high bound only change one. So how can it be? How can its time complex be log?
Or is it log?
Uh, I see in some words that this is the time complexity. I didn't
Okay.
contact.
Well, that sounds hard to believe for the following. Like, suppose the two runs are equally long, then that is just constant time. But you're supposed to merge. You're supposed to find the median or something like this. Find median. That sounds not possible.
The main I don't understand is it only trend one. How can I know the first cut is at the middle, but after that it only trend one every time. But I don't know why it's time.
Can you share the reference for that? Maybe they had some. My suspicion is they had some other assumptions.
Okay. This is a question from LeetCode.
From pardon? From LeetCode?
Yeah. But maybe later I will put the.
Yeah, I think it might be good. Yeah. It's an interesting problem. So if you have to sort a list and find the median of the two, I think it's, yeah. But I'm not sure if you can do better than something like log squared or so.
Log square is like log times log.
Yeah.
Oh, okay.
Yeah. That's what I think is a natural algorithm that you.
So this may be something wrong. This result.
I think it's for a slightly different task. You need something. You need to know something in addition, because this is constant time, but you don't know anything about the two runs. They might overlap in arbitrary ways, the values. And so I think you can probably prove that can't always get the right answer.
Okay.
The proof would be as follows, right? If it's constant time, it can only touch a constant number of elements from the two arrays.
Sorry. Can you repeat?
Sorry. If the algorithm overall takes constant time, in an instance where n and m are the same, then in constant time, I can only look at a constant number of positions in this array. I don't have time to do anything else. So you read 10 positions from the left and from the right array. And from that, you have to compute where the median is. But the algorithm hasn't looked at all the other inputs. So you can play an adversary game where you put numbers in to make the algorithm fail. And I think this might be possible, such an argument. So that's why it's.
I already tried that. The code is correct, but maybe.
Yeah, I think the
maybe
code might be fine. Just the analysis might be different. Yeah.
I will try. I will try that. Thank you.
Yeah. Thanks.
I
Hi.
can't able to register my attendance.
Let me just open the question again. Yeah. Yeah, let me show it for everyone. There's a few people who came late. So it's 807-542.
807-542.
Yep.
Thank you.
Sure.
Trying to implement tag using linked list. I've already implemented it. One thing, question was, coming into my mind. So what is the limitation of pushing the element in a stack using linked list?
There's no conceptual limit.
It depends upon the system, memory size.
Yeah, if you run out of memory, that's your limit.
Okay.
Maybe something before, but yeah. Well, for an array is as big as you allocate it.
It's actually I've just implemented it both the things. I'm going for queue. I was just thinking, how it should implement it.
Maybe share it on Campus Wire if you
Okay,
have
sir.
if you have a question.
Yes.
It's easier if you see the actual code.
Yeah.
Yeah. All right, guys. Fresh energy. A little bit left. Anyone still outside? Feel maybe a few. Right, let's slowly get started. And whoever's late has to catch up. There's always the recording. In the next section, I want to talk with you about ordered symbol tables. That's an extension of the API we've just covered and that binary search trees nicely implement. But it's an extension that drives home this point of having a dynamic array in the true sense, where you can insert elements in any position. That makes this really possible. And I haven't really commented on this after shouting it out initially. So we'll come back to that. In addition to the symbol table operations we've had before, so mainly put and get, plus deletions and so on, an ordered symbol table supports what we've implicitly assumed about the keys before, namely that they are totally ordered. A binary search tree always assumes that the keys are in some order so that you can decide what goes left and right. And an ordered symbol table exposes this order with extra operations to make it useful for the user of the data structure. So we have min and max to find the smallest or largest key in the symbol table. We have operations that find the closest to a key. If the key itself is stored, it will be returned. But if the key is not in the symbol table, you find the predecessor or successor. It's called floor and ceiling because if you think about the integers as your symbol table, then floor and ceiling in the usual way would work like this. So maybe it's a good mnemonic, whereas, yeah, that's the design decision from the book. So I just kept it that way. And then we have two more interesting operations, rank and select. Rank is given a key, and it finds the number of elements in the symbol table that are smaller, whose key is smaller. And select is the inverse operation. You give it a rank or an index, I, a number, and it finds you the element that is the ith smallest. So that also means, right, if you say select of rank of x, and x is in the data structure, in our symbol table, you would always get the same thing back. So they're built so that this works. Rank would find how many are smaller than x, and then select would give you that element back. And rank and select may, by the name, not sound like this, but you can really use those two, specifically select, to simulate something like a truly dynamic array. Because select gives you access to the ith position. So you can use this to build an array as follows. You have some key value by which you keep things sorted, and then the value that you associate with that key is the actual thing that you store in the array. And then with select, you can access the ith position in this dynamic array, in this hypothetical array. And you can insert with the usual way by specifying a key that lies between two existing keys in a certain position, and it will just take logarithmic log n time if the tree is balanced, if the height is good. Now, there's one difference to an array. If you insert something in the middle, all the indices of elements to the right of that shift. Okay, clear, right? If you have an array and I want to insert a new element in here, all the elements to the right of it will have to make space for this new element. In a binary search tree, we don't touch all these elements. That's the whole point. We're not, like in an array, explicitly copying this. This array is just mentally in your head. It's a virtual array. But still, if you want to access by index, you have to somehow keep track that all the indices have moved if you insert something in the middle. That's why ordered symbol tables don't talk about indices. They have keys, and the keys stay the same. But the ranks are dynamic. The ranks can change all the time with insertions and deletions. I hope that may become clear a bit when you use this a bit. So for now, again, that's just the definition. That's the abstract data type. How can we implement this? Before we get to that, though, let me again check whether that has sunk in. That's a simple question testing your understanding of the definition. No tricks involved. But you may want to see the definition again. You may want to see both at the same time. Now it's, of course, very small. Lots of discussions. Shall we discuss together? All right, let me show your answers. We have a peak, but we also have many other answers. Most of you are right. So the only thing to remember is that rank returns the number of elements that are strictly smaller, which is another way of saying it's zero-based. The smallest element has rank 0. So if we do this here, remember we project elements down, then we get some sorted list. So we can do that here. And I'll ignore the other ones. The one we care about, 35, is here. And so there will be these 4, 11, 12, 17, and 28, which are strictly smaller, so the rank should be 4. That was the symbol table with the sorted operations. How do we implement this? I already said binary search tree do the trick. Binary search trees do the trick. But you have to add one tiny extra little bit. And this has become known as augmented binary search trees. The augmentation consists in having another field for each node, which stores the size of its subtree, the number of nodes in its subtree, including the node itself. That's why all the leaves have a 1. This guy has a 2 because it adds itself to that one, 4, and so on. So you can double check on the slide whether I did it correctly. That's the invariant that we try to guarantee. So every node shall know how big its subtree is. I'll skip how to update that upon insertions and deletions. Again, the videos do it in detail. Let's suppose you managed to do this, and it's not too hard to do because say you insert another node here, 70. Whose subtrees have to change if you do this? Well, 70 is in this node's subtree and is in this node's subtree. Oh, it's a bigger one. And in this node's subtree, and it's in the entire tree. The roots of these trees, let me get rid of that because it's not so helpful to see, I think. The roots of these trees are this one, and this one, and this one, and this one. That's exactly the nodes on the search path. So we visited these guys anyways. So we might as well, while we do the search, increment their size by 1 because they each gain 1 new node in their subtree. So that's if we add this one here. Okay, now I just said I don't show you how to maintain it. Now I did. It's not that hard, that's the point. So how can we use this for our operations? Let's do an example for rank. We're trying to find the rank of 35. As always in a binary search tree, we'll start with a search because that's pretty much the only thing it can do. So that's always a safe bet. So we go all the way down here until we find that node. Now rank is supposed to return, as we've seen in the example, 4, right? We find the element here. Rank is the size of this. Now, how do we get this from the nodes that we have on the search path without visiting all those nodes? We don't want to pay extra. So what we'll do is we'll split the contribution of nodes that are smaller into several parts. One contribution is visited nodes that are smaller. These are the ones where we took a right turn. So it's the 12 and the 28. Right? Whereas whenever we took a left turn in the path, we know that that node was too big, and actually also its right subtree was too big. We have to add another contribution. whenever we do a right turn, like in this case, or well, we follow a right pointer, we have skipped an entire subtree, namely this one, and here we do it again. These we don't explicitly touch, but we can check how big they are by peeking into that node's size field. Okay, so in this case, this both works out to 2. But in general, these pink subtrees could have been arbitrarily big. All I need to do is visit this child and look at how big its subtree is. That's the whole magic, why the subtree sizes are useful. You can visit the node and do one check, and then you know how big the subtree is without further looking. And that's rank. So to put that into code, you would have to do the search, keep a count whenever you find a node that's smaller, whose key is smaller. And if you found such a node, you can add its left subtree. How do we do the other operation, the select operation, which is the opposite? Let's do the same example. So if you say select 4, I'd like to get this one as a result because, again, remember, this is virtual, right? This array at the bottom doesn't exist in the computer memory. All that exists is the tree. I should have stressed that maybe. This is just for us to make it easier to visualize and to think about it. All the computer has is the tree structure on top. But if I have this help, I know immediately select 4 should return the 35. But how does the computer do it only knowing the tree? Well, we do a kind of search again. We start at the root. Now, we can't really make use of the key. All we can use is the subtree sizes this time. Now, the root has 16 in its subtree. That doesn't help us, but we can peek in its left. Let me show that maybe as a dotted line. So we peek into the left subtree and get out how big it is. And based on that number, we make a decision. Now, 9 is greater than 4, greater equal, which means there's enough nodes in the left subtree to contain the one that we're looking at. In another way, it means there's too many to the left of this dividing line for our node that we're looking for to be on the right side. It has to be left. The only other option would have been, I guess I should add a +1 here, or -1 on that side, because we're 0 based. If we're looking for 70 for select 9, let's do this as a second case. Select 9. In this case, I would also peek into the left. I would find rank 9, which means there's exactly 9 things in the left subtree. That means the root has rank 9. Then I can stop. Okay. So let's write this as strictly greater. In that case, we have to go into the left subtree. So we now actually follow the search path to here. Now we're in the same situation. We peek into the left subtree and look at its subtree size. That's 1. That's too small. That's less than 4. So in this case, we have to go right. But we're skipping a subtree now. By moving right, we move into this subtree. So the remaining tree that we're looking at is only this. And there's 2 to the left of that one. So that subtree only corresponds to this range. Okay, maybe I should draw it a little more carefully. So it's only covering that part. There's 2 keys that we are skipping by going left, and we have to adjust the rank that we're looking for accordingly. So when we go down this road, we change our query to select 2. We subtract 1 for the node that we just skipped, and we subtract 1 for the subtree size that we skipped. These are the exact same 2 values that we had before. I called this the green and this the purple one before. So we skip this and we skip this. Then within this tree, we do the same procedure. We're trying to select the node of rank 2. Where here we peek into the thing. 4 is bigger than 2, so we go to the left subtree. If you go left, you don't have to adjust the rank. That's the easy case. We're still looking for rank 2. We peek into the left. 1 is too small. So again, we take a turn right. But we have to select 0 now, because again, we omit these 2. The entire subtree and this node are removed from the consideration. And now we're down to this small part. And now if you say select 0, here there's nothing on the left subtree, so the root has rank 0 in this subtree. So we return 35, and that's what we wanted. Okay? So select from all the operations is the one that's most intricate, because you have to combine all the things that we've done before. But once you're over that hurdle, you have this fully dynamic array where you can insert things in any point, and you can jump to any position, all bounded by the height of the binary search tree. In this case, I told you the solution without motivating why that's the solution first. And I want to finish off by telling you why that is the solution. The solution being augmenting the tree with subtree sizes. It looks like this made select rather tricky, so maybe there should be an easier way to do it. So for example, you could, instead of augmenting the tree with subtree sizes, store the rank of every node in each node. That would be super handy, because then rank is trivial. You just find the node and return the stored rank. And select would also be easy. You just do a binary search based on those stored ranks. If someone wants to shout out why that's a bad idea, you could do. This would work fine for the static problem, but not if you want to insert and delete things. So you can't really maintain this efficiently. And if you draw a small example, it's obvious to see why. So suppose on the right-hand side, here's a really big subtree. And now suppose I insert a new node here. What does that do to all the ranks to the right of this red node? Well, they all have to go up by 1. I have to increase their rank by 1. If I explicitly store the ranks in nodes, I have to touch all those nodes. I have to explicitly visit them and update their rank. And I just don't have the time to do that if I want to be fast. This could be essentially the entire tree. And so we're back to linear time. Whereas subtree sizes have this lovely property that they're local. Only on the search path does the subtree size change. Right? So subtree size is only changing here +1, here +1, and here +1. And I don't have to visit all of those guys. It's just one path. Good. Let me briefly go over the questions that we had on Slido. Okay, I have to stop the poll. So one question was about why 77 is the root. That is depending on how the tree is built. So assume that we start with an empty tree, then the first thing that gets inserted would become the root. And whoever is the first thing to be inserted is chosen as the root and stays the root for good until they're deleted. So in a sense, it's arbitrary for the example. I just tried to pick one where all the weird cases occur. And 77 sounded like a good number. Second question is about whether we always need numerical keys. And the answer is no. I picked numbers for the examples, again, because humans are very quick at deciding this number is smaller than that number in our usual decimal system and so on. It can be any object where you can define an ordering relation. So it could be strings sorted alphabetically. It could be your custom object sorted by whatever fields it has. It can be, it should be a total order. What else could there be? Like it could be people sorted by birth date, by age, or stuff like this. Right? If the root is deleted, depends on what it is, but it's one of the three cases. It's either a leaf, then it's a tiny tree, or it's unary, or it's a binary node. One of the three cases applies, and it's same as, there's no special case for the root needed. Okay, I'll put that off for a campus wire, I'd say. You can watch the recording again and check, and if you still have questions about select, take them to campus wire. If I say the same thing again, I'm not sure if that makes it more clear. So I'd rather be more targeted. If you have specific questions, obviously these are welcome, and many, probably other people have them too. There's only a tiny piece of Unit 2 left. And that's really just a comment that this would be another substantial chapter in an undergrad algorithms class. And I'll cut it short to basically just this announcement. In the last little bit of Unit 2, we'll talk about balanced binary search trees. And this is really just a teaser of what is possible. And I suppose for many of you, that will be just repetition. No, sorry, I started the wrong one. There we go. I'll have a list of things on the slide in a second. So the way the question is posed as an open answer thing, we'll probably get a cloud of words without much of a sense of what percentage of people have seen it before. But it's roughly a quarter in the class who have not done an undergraduate degree in computer science. And those are unlikely to have seen balanced binary search trees, whereas everyone who has a computer science undergrad degree is very likely to have seen one variety of those. So I can pretty much predict it will be between 2/3 and 3/4 who have seen it. We will continue tomorrow. Is that actually meaning we should stop now? Of course not. I'll keep the collection open. We can have a peek at it. Here's my list. It's probably not complete. Let me jump to this. So AVL trees and red-black trees are by far the most widely used and widely known ones. There's a few others, and then there's a few more. But let me take a step back and what are we talking about here, if you haven't seen this before. So all of today, I talked about, binary search trees are so cool because the operations are fast. But the operations are only fast if the tree is not too tall. And then I promised you if the keys come in random order in the insertions, everything will be fine, fingers crossed. But if they don't come in random order, it might be linear time. So the worst case for a binary search tree, if the insertion order is not controlled for in any way, is pretty poor. Instead, we'd like to have log n time regardless of the insertion order, in the worst case. And that is possible by various schemes of keeping the tree balanced, where balanced is essentially defined as anything that has height at most log n in all the subtrees. So the typical way to do this is to impose an invariant on the shapes that are allowed. We've seen an invariant on shapes in the heaps chapter. There, the invariant was very simple. Every binary heap shall have exactly this shape if it has n nodes. We'll have to be a bit more lenient with binary search trees. That will not be able to maintain such a strict invariant. But essentially, AVL trees and red-black trees and weight-bound trees, these are all types of invariants on the shape of the tree that you can maintain. So you have certain rules or certain extra steps for the updates, insertions, and deletions that re-establish that invariant. Just to make it concrete, for AVL trees, the invariant that we have is as follows. If you have any node, then it has potentially 2 subtrees. And then the height of the 2 subtrees, say if this is the left height and this is the right height, then they may differ by at most 1. That's the condition for AVL trees, and this shall be true at every node. So for every node, the difference in subtree heights is at most 1. It might be a bit, it might need some thinking how to maintain this, and this is another 2 hours or so of lectures to do it, so I'll not do it. But you can watch the videos, which don't touch AVL trees, they touch red-black trees. That's a slightly different variant. I'm not going to define it formally. It's a similar idea. You keep some certain invariants. And it's a little faster to implement. That's why people prefer it. The Java library has red-black trees. Same for the C++, STL. Python famously doesn't have binary search trees built in. Big shame, but there's extra libraries. There's a few others. There's another option. Instead of having these invariants on the shape that somehow need to be maintained, there's other options that also can work. I just want to throw these out because they're ideas that are interesting beyond just binary search trees. One is amortization. We talked about this before for the doubling arrays. Amortization is the idea that some operations might be expensive, but if you have a long sequence of operations, on average, each operation is cheap. Splay trees are the prime example where a somewhat magic rule how to change your tree guarantees that if you have a long sequence of updates, they will always come out cheap. There's actually a deep open question, open for 40 years in computer science, that people are still struggling with, whether splay trees are the best way to do this kind of update. I can tell you a bit more about this offline if you're interested. It's very fun and a really cool research topic, but it's beyond the scope here. I just think it's useful to know that these exist. They have some properties that are useful in that they don't need an extra field. For AVL trees, you essentially have to store the height of these subtrees, and splay trees avoid that. The second option is randomization. What I said previously, the height is usually good if the insertion order is random. You can do better than that. You can enforce the randomness. So even if someone inserts things in a bad order, it's still unlikely that you see a tall tree. But you kind of enforce the randomness by explicitly doing random things. It's very different and much more powerful. Again, some of these are useful in specific scenarios, like skip lists are good for concurrent data structures and so on. But all a bit beyond the scope here. Just want to throw out a few things that if you feel that unit was a bit underwhelming because you've seen all that before, there's a lot of cool stuff that ties into this and that's worth looking at. I have one big slide to summarize what we've done in this module, in this unit. We talked about priority queues on that side, the binary heaps, and we've talked about symbol tables or ordered symbol tables and binary search trees. And here are all the running times that we achieve. So here, assuming a balanced binary search tree, any of the ones from the previous slide would do. And if you look at this, you might wonder why people are at all excited about heaps. Because essentially, all the operations that a heap can do, like insert and removing the maximum, a binary search tree can do that too in the same time. So how would you do delete max in a binary search tree? You could do min and max in logarithmic time, and then you can do a delete afterwards, logarithmic time. So factor 2 slower, fine, but apart from that, if you just look at the big O statements, it's the same. There's one exception, and that's the first line, the construction. If you want to build a heap from a set of elements which are not in sorted order, you can still do it in linear time. We discussed this with the build little heaplets and do the sync. For a binary search tree, you cannot do that. And soon we'll prove why. But that seems to be the only thing. So you might come out of this, or some of you may have come out of an undergraduate algorithms class feeling a bit cheated. Why do people care about this priority queue abstraction if the best we can do, binary heaps, are not really faster than the general purpose binary search trees that can do that at the same time, plus a lot of other operations? And my counterpoint to that would be the abstraction of a priority queue is still useful. One, it can express that you only need certain subsets of the functionality, but two, there are better implementations. So the reason you don't hear about those in most algorithms classes is that they're incredibly complicated. And so for the state of the art in research, I know that there's an educational implementation, but not one that beats binary heaps on small inputs. But at least in theory, it's possible to support the priority queue operations much faster, so that only delete max is logarithmic, whereas insert and change key is constant time, and that's even in the worst case. And for various reasons that we'll talk about in the sorting chapter, that's completely impossible for binary search trees. So there's a clear separation between those two abstract data types. And so it can be useful to keep those around, even if the best implementation you currently have doesn't seem to get you any edge. Good, that's all I have to say about fundamental data structures. We'll start with sorting tomorrow. Fresh new topic. We'll start with basic stuff. So first half an hour, probably a few of you will again go to sleep, but then it's time to wake up, or maybe 45 minutes. Then it's time to wake up for some new and exciting stuff that nobody has seen, but it's easy to follow.